Our second lot of hydrocarbons that we need to know something about are alkenes, and basically you don't have to know a lot more than what we had last year. Like with the alkanes, the introduction of cyclics is the new thing, really. Okay, we call them unsaturated hydrocarbons or unsaturated compounds. What does unsaturated actually mean when we think about their properties or their reactions? What does that actually mean?
They can undergo addition reaction.
Great. They can undergo addition, and this is because they can have their double bond broken and something added to it without anything being removed. So that the functional group that they have, what we call the functional group, is this carbon-carbon double bond. It can break with enough energy to have something added to it. And actually, the presence of a compound like bromine provides enough energy in itself to break that and have a bromine atom add to each carbon. So that's probably our first of the interesting compounds, really, because the alkanes are pretty boring. The hydrocarbons part means we're only looking at hydrogens and carbons. So you can see all these apexes or corners that I've got. If I can only see hydrogens there, it means that these are abbreviated structures for that, showing the carbons as just a corner. You'll see as you get further on, I might draw, for example, what's called cyclopentene. I might draw that just as a pentagon with a double line somewhere. Okay? And that's the way you'll see it at university if you're going on there. Alright, we don't tend to do all the hydrogens when we're doing these skeleton structures. At this stage in assessments, you probably should be looking at putting the carbons in for anything that's straight-chained or branched, which is straight chains with methyl groups and stuff coming off it. But with cyclics, you'll get away with just drawing a shape, so you don't even need the hydrogens on it. The reason I put the hydrogens is to help us count them, to see what we've actually got here. So for our straight chain and branched ones, these are both straight chain because there's no methyl groups coming off them. We've got two corners, as it were, so it's two carbons. That should be an N, sorry, I just noticed an error. Should be a fix. So we've got C2H4. We've got 1, 2, 3 carbons here. So C3 with 1, 2, 3, 4, 5, 6 hydrogens here. You can see this general formula being done. The number of carbons is just doubled to give you the number of hydrogens. If you see something with that formula, where there's twice as many hydrogens as there are carbons, it means it's either an alkene or what else could it be?
Cycloalkane.
Good, could be a cyclic alkane. For these ones here, you'll see I've got 1, 2, 3, 4, 5 pentagon. So I've got 5 carbons. But I've only got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. With this one, I've got 6. It's a hexagon, so I should hope that there's 6 of them there. But only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. And so what I find is, if I get a whole series of these, a homologous series, so a series of chemicals with the same functional group, that's what homologous means, then I find the same pattern. If I double it and subtract 2, I've got the number of hydrogens. Okay. The naming of these is actually quite easy. We'll start with the straight chains. Remember that meth, eth, prot, bute, that counts for all organic compounds. So I've got 2 carbons. This is eth. Alkenes end in E-N-E. So this would be ethene. Ene for the double bond, eth for the 2 carbons. This one has got 1, 2, 3, so it's prop. It's got a double bond, so it's propene. Once you get beyond propene, so butene and on, for straight chains and branched, you must say where that functional group is, where the double bond is. I'll show you that in a moment, because I'm going to use butene to demonstrate structural isomerism and geometric isomerism in a moment. For cyclics, you don't have to say the number that they're on, because they've only got 1 double bond. If they have more than 1 double bond, they've got some different ways of being named, and you won't be exposed to those this year, so don't worry about them. So, because I've only got the 1, in it doesn't matter which one I call carbon number 1, that's the one the functional group will be on. So this is just called cyclopentene. Alright, so guess the name of that one. Cyclohexene, excellent. This is a chemical, cyclohexene is a chemical you're going to use on Monday when you do your experiment to see if you can use experiments to tell alkenes and alkanes apart. I'm going to give you cyclohexane and cyclohexene, give you a range of chemicals. Some of them will be what we call red herrings, chemicals that won't help at all, and some will be chemicals that will really help, and for you to work out which chemicals actually do help. Okay? I won't go any further than that because I want you to have a bit of fun with it. Okay, now I said I'd revisit butene for a really good reason. Butene has got the formula C4H8. And the reason I like using it is it demonstrates structural isomerism, so different ways of laying the atoms out, the carbon-carbon bonds, and it shows a thing called geometric isomerism. The carbon-carbon single bond can be rotated in three-dimensional space, which means that if I draw it one way and it can look a different way, it's often just that it's twisted. Okay, it's just been a rotation, because things move. That's naturally what happens. A carbon-carbon double bond is rigid. It cannot twist and turn. So what this means is if there's a hydrogen and its electron cloud up here, that's where it lives. It can't move anywhere else without the whole molecule twisting. So relative to everything else, it's in the same place. So because of the double bond being rigid, if I have different groups on the carbons, so two different groups on the same carbon, two different groups on the same carbon, then I can have a thing called geometric isomerism. You might hear it called cis-trans isomerism or EZ isomerism. EZ is an older way of naming it. It comes from two German words, entgegen, which means opposite, and zusammen, which means together. So zusammen or Z is cis, if you've met cis isomers before, and entgegen or E is trans. Right, so I'm going to start with this one by making a thing called 1-butene. So I'm going to put the double bond on the very first carbon. Okay. One, two, three, 4 carbons. I could number it the other way. I could go 1, 2, 3, 4, but my goal is to get the functional group numbered as low as possible. So this can be either carbon 1 or 4. If it's 1, then it's 1-butene, which is the correct name. You might also see it named as but-1-ene. Both names are equally correct. You are allowed to use either. So I'll write that as well. But-1-ene. I don't like it because my ones look like owls, if I'm honest with you, and can look a bit ambiguous when I'm writing at 3 million miles an hour to get my exam written in time to get on to the next achievement standard. Alright, I like to write it 1-butene because it's a little bit less ambiguous. That's all. It's my only reason for the preference. Now, I could move that double bond across into the middle, and that will make 2-butene. So I'm going to put an H there, and this carbon is now going to be here, CH3. And now, where should I put the other hydrogen? Top one or the bottom one? Does it matter? Let's say it doesn't matter, okay? And let's see what happens. These compounds are both CH3, sorry, I'll write it as I do it because I know it becomes hard to imagine. They are both CH3, CH, CH, CH3. Would we agree with that? That's their expanded formula, basically, expanded molecular formula. Okay, CH3, CH, CH, CH3. They're the same. But if you look at them, they take up space slightly differently. The space they occupy, the three-dimensional space when you make these molecules in a moment, is different. So we have to have a way to tell them apart. We have to have a way to tell them apart by naming them as well. So first of all, they're both examples of 2-butene, or but-2-ene. So whatever I am going to do, I still need that name in both of them. Now, the double bond is the key to this, and so we use it to help us name this. The double bond is rigid and cannot be rotated. Okay, we can't just spin that around to become that. We're not allowed to. Well, it's not. It's physically impossible. That cannot be done. This carbon has 2 different functional groups on it. This carbon has 2 different functional groups on it. This is why geometric isomerism can exist with this molecule. Yes?
So structural isomerism is when you have the functional group on a different carbon.
Perfect.
And geometric isomerism is when you have cis and trans.
Spot on.
Over a double bond.
Spot on. And there is one structural isomer of this I haven't shown you yet, which is methyl propene. Okay, where I'd move this one and put it on there.
Yeah.
But I'm going to run out of space for that. So there is another structural isomer. So it's either moving the functional group or having methyl groups off it. Yep, good question and good comment. Okay, so what I do is I use the double bond to help me determine which of these cis or trans it is. And the way I like to think of it is the cis is creating a letter C when I look at being consistent with the same functional group. So I could look at the carbon chain. That's the way I like to do it. I'm going to follow the carbon chain through with my red pen. And that carbon chain is making, albeit a bit ugly, on 90 degrees, the letter C for that one there. See my carbon chain making the letter C? So therefore, I think it's a pretty fair call to say that this is cis 2-butene, because cis starts with the letter C. In this one, however, I'm going to go through here. I'm going to go from one to the other through the double bond. And the prefix trans normally means to go across. Transit, transverse, those sorts of things. So this is going across the double bond. So this is trans 2-butene. Now if you name it without the number, or if you name it without the cis or the trans, it's incorrect. So that's really important to remember. So, just to recap, we have alkenes are unsaturated, which means they have a double bond. That's really important because that gives them a lot of their chemical properties, particularly that they can have addition reactions. It's also important because structurally it's a rigid bond, it can't rotate, which means that as well as having structural isomerism like all other organic compounds, particularly of 4 carbons or more, you can also have what's called geometric isomerism, where the actual layout in 3-dimensional space is different, even though they have the same formula. Even though they have the same formula, and even though the double bond is in the same place. For this to occur, there must be a double bond, of course. And the carbons involved in that double bond, each carbon must have 2 different things bound to that carbon. So this carbon's got an H and a CH3. This one just happens to also have an H and CH3 bound to it. But the H and the CH3 are different things, so cis-trans isomerism can occur.
What happens when there are 2 CH3s on the same carbon?
Right, so I will go to that methyl one, then I'll just squeeze it in. So I'm just going to sort of show that it's something different. So sort of, really good question. So if I go to that one that I mentioned when we had that question before, and I've got, so for that you'd have now I know this is different, this has got 5 carbons, but for this it doesn't have cis and trans because that's got 2 things that are the same on it. Okay? If I get rid of this one and make it a hydrogen, so it is an isomer of this, our biggest carbon chain is actually only 3 carbons long. So it becomes propene. It doesn't matter where I have the double, well it does matter where I have the double bond. So here I've got a 1 propene because this will be my number 1 carbon. So I'll end up with 2 methyl, because this is now a side chain with 1 carbon in it, 2 methyl, 1 propene. Okay. Now, I don't need the 1 because if I put the double bond there, the 3 becomes the 1 because I can number it the other way. All right, so really good question. This does not have cis-trans isomerism because each carbon, in particular we're focusing on this one, this carbon has got 2 things that are the same. Cis and trans can't happen. Now, it's not just that it's carbon, it's CH3. If this was CH2CH3, this was CH3, and say this was CH3, that would have cis-trans because you'd follow the biggest carbon chain. All right, it'd be the one with extra stuff in it. Okay, it's a very good question. Any other questions about that?
How much does geometric isomerism actually affect the chemical effects of them?
Chemical, not so much. Physical, though, it does. Because cis isomers tend not to be able to be packed so tightly together. They have different melting and boiling points, quite often in different densities. Because actually, geometrically, they don't slot together like jigsaw puzzles quite so nicely. Trans isomers tend to work quite nicely. If, let's say, instead of CH3s, these were chlorines, this one would be non-polar because the dipoles would cancel, but this one would be polar because they would amplify each other. So you can have difference in polarity as well. All right, so it doesn't affect the chemical reactivity so much, but it does affect some physical properties if there's polar groups involved or very big electron clouds involved. All right, might stop that there.